Okay, welcome to this week's hottest seminar. Our speaker this week is Jonathan Weinberger, and he will be telling us about directed univalence and the Yoneda embedding for synthetic infinity-1 categories. Please go ahead, Jonathan.
Thanks for the introduction, Dan. So I'm going to talk about joint work with Dan Gratzer and Ulrich Buchholz. And so this is kind of recent work, but I'm also going to talk a little bit about a formalization project, also not from too long ago, together with Nikolai Kudasov and Emily Riehl. So first of all, I'd like to dedicate this talk to the memory of Thomas Streicher, who sadly passed away just this year. He was my PhD advisor at TU Darmstadt when Ulrich also was there, and we have had many discussions with him about various themes, including some very early stages of some of the work that I'm going to talk about in this talk. And I know that he is missed by many in the community. Okay, so I'm talking about a certain approach to infinity-1 categories in a synthetic type-theoretic way. So in an infinity-1 category, kind of intuitively, is somewhat similar to a 1 category. So we have a notion of objects and morphisms, but the morphisms, the composition of morphisms is defined only up to contractibility, so up to a contractible space of composition data. Another way to think about this is that instead of just sets of objects and morphisms, we actually have spaces of objects and morphisms. And this kind of defineness up to contractibility yields to coherence data of the it leads us to having to sort of keep track about the higher coherences of the compositions. So whenever I say infinity category in that talk, I really mean infinity-1 category, meaning that all the potential n morphisms for higher n are in fact all invertible. So a long-standing question had been, we know that homotopy type theory is a great synthetic theory for topological spaces up to homotopy, aka infinity groupoids. So we have the path types that have a lot of good structure, but what about directed Hom types? So what about kind of having the possibility of not necessarily invertible arrows? So there are several possible approaches to type theories that capture this genuine sense of directedness. So there's very early work by Warren, Licata, and Harper, and then later work by various other people and groups of people that I've listed here. So not everything necessarily has the goal to talk about infinity categories as opposed to just 1 categories, but what they all have in common is that they kind of propose various setups for directed type theory. And okay, so I'm going to focus today on a specific framework in which this is possible. And this framework is also related to other synthetic approaches to now really infinity categories, namely the Infinity Cosmos project by Riehl and Shulman, the kind of synthetic infinity category theory by Szynski, Knossen, Yen, and Balde, of which we've also seen a recent hottest talk, and the internal infinity topos and category theory by Martini and Wolf. So all of these theories here are also synthetic in a certain sense, that the infinity categories are kind of native objects, but they are not formulated in a type theoretic setting or in type theoretic setting per se. So in our work, we focus on Riehl Shulman's Simplicial type theory from 2017, but we also take many influences from infinity cosmos theory, but also these kind of recent works that I'm mentioning here. And then there's parallels in particular to the bicubical directed type theory by Weaver and Licata. So what I'm going to introduce now deviates a little bit from the recent write-ups that we have on this with my co-authors. So I'm presenting a version of the theory that is a bit closer to the original Riehl-Shulman development, so it's a little bit stricter in the following sense. So to introduce this like sense of direction, meaning non-invertible arrows, first of all, what we have to do, we have to introduce a directed interval into the theory called delta 1, together with all its powers, giving rise to the point, delta 1 itself, and then the square, delta 1 cross delta 1 that I haven't put here, and then all the kind of higher dimensional cubes. And then we're also we're allowing ourselves to basically carve out retracts, so subshapes of these objects, modeling the composition data that we are interested in capturing later on, such as the boundary or the two one-horn, which is this pair of two composable arrows. And then with regards to the strictness that I just mentioned, what we want to do is we want to kind of capture what it means for sections of a family that is defined on a shape like this, for what it means to have a given a partial section A like this that is defined on the subshape, we want to reify all the possible extensions to sections over the total shape. We want to reify all those extensions into a type, enforcing strict judgmental behavior. So these extensions should really be judgmental extensions and not just propositional ones. So definitely parts of the theory can be reformulated using a kind of weaker version where you'd actually have identity types here and are able to define the extension types just natively in HoTT. Again, of course, using these additional shapes that we have just added. But having the strictness maybe doesn't do much harm. In fact, one can internally prove that if you have these strict extension types under the usual kind of function extensionality assumptions, then the strict extension types coincide with the weak extension types. Okay, with this, we can define a notion of harm type by saying that an arrow should be just an image of the interval in a type that restricts to the points on the boundary, the points that we want to have a morphism between. So a morphism from A to B in a type is given by all possible maps from delta 1 to B that strictly restrict on the boundary to A and B in the according order, of course. And the nice thing is we're in type theory, so we can relativize this. So having a type family and some arrow in the base type, we can look at all the possible arrows that pass through the fibers and lie strictly over the type in the base type, the arrow in the base type. So the image you can have in mind is something like this, which of course also suggests these extension types are really defined for all these possible shapes that we have in the theory. So you can look at kind of triangle lying over triangles or two one-horns lying over triangles or something like that. So with this, we can now say, according to Riehl-Shulman and kind of earlier work by Jayal, that a type is a pre-infinity category or a Segal type if it has weak composition in the sense that this restriction map that restricts a triangle that witnesses the composition to just the pair of two composable arrows, that this be an equivalence. To get actual infinity categories, we have to add a completeness condition, which says that the two conceivable notions of isomorphism actually decide. So on the actually coincide. So on the one hand, we could look at identifications or paths in the type, and on the other hand, we could look at isomorphisms, which are a derived notion that we get from the Hom types as kind of bi-invertible morphisms. There's a canonical comparison map, and if this is an equivalence, then we do actually get the right synthetic notion of infinity category. And if we just ask the map to the map that converts a path to just a homomorphism without caring about if it's an isomorphism or not, if this is an equivalence, then we get synthetic infinity groupoids. So the idea is that kind of HoTT embeds into Simplicial HoTT via this predicate in some sense. So, and this all can and has been made more precise. So just as every infinity topos admits a model of homotopy type theory, as per Mike's major result from 2019, every infinity topos of simplicial objects admits a model of Simplicial HoTT. So this notion of synthetic infinity category theory interprets into ordinary infinity category theory, and at least some parts of it, I mean, so that holds true if we instantiate the base with the ordinary infinity category of spaces, and at least, you know, some, if not many parts of the theory actually internalize with respect to replacing the base by more general toposes or by other toposes. So, I mean, so far, both of these hold true, but in the course of the talk, I will add more structure and more axioms. And for now, I don't want to claim that all of those kind of carry through, but I will claim that all of those definitely carry through for the standard model over spaces. Okay, so these Segal types or Rezk type synthetic infinity categories have some very nice behavior, a lot of which just falls out of the theory. So one can prove that the Hom types of a Segal type are groupoidal. So they are spaces in the usual homotopical sense, meaning that we recover this kind of notion of infinity categories enriched in spaces from that. And moreover, we can actually prove that we get a category in the expected sense rather than imposing it. So by this, I mean that just from this definition of having composition in terms of the Segal condition here, we can prove associativity, for instance. And we can also prove that we can basically compute the type of natural transformations to being equivalent to the usual definition. We don't have to say what a naturality square is. We can, it's something that falls out of the definition just in the way that it's set up and the way that these extension types work. And in fact, every function between types that happen to be infinity categories in that setting is automatically a functor, meaning it preserves composition, which is not that hard to see, but it's still kind of good to note because this has some implications. I mean, we get a lot of naturality for free, which is nice and which I think is a great selling point for that theory. On the other hand, it becomes harder to do things that are, much like in homotopy type theory, that actually are not invariant, right? So sometimes kind of in set-based mathematics and in particular higher category theory, you have to do things that like lead you out of the fibrant layer, that don't respect equivalence or that maybe not necessarily respect equivalence. And sometimes that's what you want to do to get a certain construction to work. So the kind of price we're paying here that we will have to extend our theory even more, which I will get to talk about in a little bit. So in particular, we want to kind of lift this idea from homotopy type theory that type families are fibrations, meaning that they have path lifting or path transport property to this categorical setting. So the right notion here would be the notion of Cocartesian or Cartesian type family, where an arrow in the base induces a functor between the fibers of the family. So this synthetic version of Cartesian families has been studied by Ulrich and myself, kind of building on earlier work by Riehl and Shulman on the discrete, the groupoidal version, which they call covariant type families, or you could call them also synthetic left fibrations, if that name is more familiar. And I want to focus on those today because I eventually will want to talk about the kind of usual Yoneda lemma, which is about these left fibrations because they model presheaves. But the kind of intrinsic way to define them is as follows. So we call a type family covariant if given an arrow in the base and a term in the fiber over the source of that arrow, we can uniquely lift the arrow in the base to a dependent arrow uniquely up to contractibility. Another way to say, I mean, there's kind of a way to express this in terms of orthogonality with respect to the left endpoint inclusion into the interval, which also is very useful to know. And there's a bunch of things that Emily and Mike figured out about these Cocartesian families. So they satisfy all the standard properties that you would like them to satisfy. In fact, from this definition, you can conclude that if the base is Segal, then the fibers will be groupoids. You get that the lifting maps compose in the natural way, and they also satisfy naturality with respect to fiber-wise maps, which then act as kind of natural transformations in some sense. So the prime example of the covariant family should be the co-representable functors Hom A in the first variable. And in fact, they could show that those are actually covariant. So there is a way to kind of say what the Yoneda lemma is for those covariant families. So this is like a fibrational Yoneda lemma, and it bears some formal resemblance with directed path induction, only that directed path induction basically comes out of the elimination rule for the identity types, and the covariant families Yoneda lemma is really something you'll have to prove using a lot of these results from synthetic infinity category theory in that setting. Just to say something about this proof, what's particularly nice here is that, I mean, it really corresponds to the fibrational Yoneda lemma for kind of left fibrations in the semantical side. So it's something genuinely infinity categorical, but its proof in this synthetic setting is easier than the proof for the one categorical Yoneda lemma is. For instance, I mean, the kind of harder part in the usual Yoneda lemma for one categories is to define this map in the other direction, and then proving that it actually lands in the type of natural transformations. Here, the type of natural transformations is just some pi type, and we can just write down the map by the covariant transport operation, and only have to check that this in fact is well typed, which is not that hard to see, and that's it. Since we get naturality for free, there's nothing more to check. So of course there are some things to check to prove that you actually get an inverse in the two directions, but arguably this is kind of less work than the one categorical, like at least in this segment of the theory. The actual proof part of the Yoneda lemma is less work than it is for the one categorical version. And this also works for Cocartesian families. That's what we proved with Ulrich a while ago. But this version for the discrete case we have by now formalized in the Rzk proof assistant. So I have some code snippet here. So the syntax is sort of akin to Agda. So this is what the definition of the Hom types would look like there. And the Rzk proof assistant is a relatively new kind of proof checker by Nikolai Kudasov. It's completely open source. And together with him and Emily, we formalized the Yoneda lemma, including all the results that were needed for it, in particular, all the kind of standard homotopy type theory results that we have needed for this. Ever since, there has been efforts involving many other contributors to expand our library for Simplicial HoTT. So anyone who's curious about this, feel free to check it out right here. Okay, so quite a lot of theory by now has been developed in that framework. So I mentioned these two items. Cesar Bartemiano has developed a theory of limits and colimits in this setting, as well as some results about exponentiable fibrations, Condorcet fibrations. We have the formalization and more contributions. But everything, I mean, there's some major kind of shortcomings of the version of the theory as I've described it so far, because there are no really constructible examples of infinity categories that are you know, not just actually one or like truncated somehow. So that is of course up to maybe someone tomorrow comes up with solving the coherence problem in HoTT. So then the story would look different presumably, but otherwise it's just not clear how to, for instance, define the infinity category of small infinity groupoids or small infinity categories in that setting, which are of course very important if we just want to even formulate standard results like the Yoneda lemma or define presheaf categories or something like that. So in some sense, we have one half of the story if we just kind of want to stick to the fibrations, but then you know, a lot of category theory still isn't captured by that. So how can we solve this? That's where multimodal dependent type theory comes in. So this in itself is a whole other topic, and people such as Daniel have already talked, given quite a few talks about this. So this is a framework that has been devised by Daniel, Gratzer, Kavvos-Nuyts-Birkedal in 2020. There had been kind of earlier versions in some guises, and of course, I mean, the story of kind of modal type theories goes back longer than this, but what's striking about this version of the theory is that this is a really nice and functioning framework where we understand the semantics and the meta theory quite well due to Daniel's PhD thesis that captures modalities like not just one modality, but a whole range of modalities that are connected in some way, and also in a dependently typed way. So what do they have to do with the story that I'm telling? So the point is that the reason is that we're interested in the modal operators is because they allow us to introduce operations that otherwise it would just not be clear how to import them. And I'm going to tell you what those are. But first of all, I mean, I mentioned one of the problems we're trying to solve is to define these universe types, such as the classifying type for the left fibrations, which ends up being the infinity category of groupoids. And to do this in an internal way, to actually construct this from something more primitive, from the actual plain universe of, you know, the simplicial space of simplicial spaces, we have to kind of embed our whole model of simplicial types or simplicial spaces into actually cubical spaces. So we kind of introduce this cubical outer layer for a reason that I'm going to explain in a second. And then we're going to add a bunch of modal operators. So first of all, we're adding simplicial localization, which is the sheaf operator corresponding to the subtopos of simplicial objects, within the cubical objects, we're adding an opposite modality, a twisted arrow modality. We're adding the discrete co-reflection and the co-discrete reflection, as well as exponentiation with the path type as a modality for somewhat technical reasons. But we're also, in particular, internalizing the right adjoint to this operation, which is a very peculiar property of the cubical interval that the simplicial interval doesn't have. And this amazing right adjoint is what will play a crucial role in constructing these universes. So this is the reason why we are kind of extending our outer theory to be cubical. At least for the time being, once we've bootstrapped everything, for the most part, it will be fine to just work internally to the cubical, to the simplicial layer. But if we, to even bootstrap the theory with respect to something, we kind of have to do this enlargement first. So this is the kind of essentially structure that we're adding, but then we also need a bunch of axioms about the interaction between those modalities and the simplicial and the modal structure. So to get an intuition for what these modalities are, the opposite modalities gives us back a type in which the n simplices are reversed. So for categories, you get the opposite category. The discrete co-reflection flat gives us the maximal subgroupoid of a type or of a category. Then we have the co-discrete reflection, which in the kind of global case corresponds to localizing at the boundary inclusions. And the twisted arrow types or categories give you kind of something like the arrow category, but the arrows, instead of looking like squares, they look like squares where you've reversed one side in the horizontal direction. So they become kind of what we call twisted squares. So these modalities internalize endo functors on our category of cubical or simplicial types, and they have ways in which they interact with each other, which is going to be what's captured, which is going to be captured by what's called a mode theory of the multimodal type theory. So the multimodal framework is really comes equipped with like a rather strict mode theory, which basically allow you to have a relatively painless handling on the ensuing deduction system. Okay, so we call this kind of maybe not so familiar framework of like simplicial within cubical type theory, triangulated type theory. So this doesn't have anything to do with triangulated categories. This literally, I mean, maybe it has a similar geometric intuition, but it really means nothing homological, but just the idea is that a type is simplicial if it can be triangulated. That's what's captured in the name. So the axioms are, and I don't want to spend too much time on all of this. The axioms first of all, we need an interval, which now we don't assume to be totally ordered, which is what distinguishes the cubical from the simplicial layer. And we also assume that we have an anti-automorphism of that interval lattice given by a reversal. Furthermore, the two conceivable notions of discreteness should be the same for the crisp types. So a type should be kind of discrete with respect to the discrete modality if it's discrete with respect to the interval. We also, from time to time, need to assume that the interval actually only has exactly two global points. Another crucial axiom is to kind of internalize the idea that a map between simplicial presheaves or cubical presheaves should be an equivalence if and only if it's a level-wise equivalence. This is what we're imposing with the cube separate axiom. We have to impose some structure on the twisted arrow modality because otherwise there's not that much that we can prove about it. In particular, well, this setup basically serves the purpose of, making the n simplices to be exactly these two n+1 simplices in the original category as desired, together with projection maps, which then we can use to prove that we actually have a left fibration, which is what we need for the Yoneda, for the categorical Yoneda lemma to work. And then we have a version of a kind of Coq-Clavier type axiom that has been, that's something that kind of comes from synthetic differential geometry, but it has been investigated in like internal algebraic geometry in Toposis by Ingo Blechschmidt a while ago, and is now also employed in this more recent work by Cocartesian et al. In Sweden for synthetic algebraic geometry. Okay, I mentioned that simplicial sets are an essential subtopos of cubical sets. This has been kind of investigated in various works by various people. And again, we are not so much interested in this kind of cubical layer per se, but we needed to bootstrap our constructions. So how does this help us precisely? We want to define the universe of spaces. So the classifying fibration for small left fibrations, fibrations with groupoidal fibers. And the kind of very naive idea would be to look at the universe that we get from the sigma type over the standard universe of cubical or simplicial spaces with respect to the proposition that says that a single type should be a covariant fibration, which then in particular means that, okay, the terms of that type would be groupoids, but there are various problems because like this predicate kind of degenerates, if you apply it to just a single type, it degenerates to not seeing the direction anymore. So you can't distinguish anymore. I mean, a groupoid is a groupoid. There's no such thing as a covariant or contravariant groupoid, but this difference, comes up when you look at the relative case of a type family. So you would lose track of the variance. So you do get a type whose terms are groupoids, but the arrows are something much more complicated. And definitely this is far from being a category. So the solution for this is the formalism of amazing fibrations, which is our name for what Mitchell Riley in recent work calls new fibrations, I think. So Mitchell's work hinges upon earlier work by Licata, Orton, Pitts, and Spitters, which used, in the context of cubical type theory, this tiny interval to construct a fibration, like a classifying type for fibrations internally. But their construction has certain caveat. You have to construct it to these crisp, the externally quantified fibrations. And one kind of improvement that this work presents here is that you can remove this crispness condition when it comes to the kind of classifying equivalence. However, you will then have to introduce a kind of stronger, more refined notion of vibration with respect to which you're classifying to. And those are exactly those amazing fibrations. So basically the problem is that just the simple covariant predicate doesn't see variance or even just dependency on the context, but the amazing fibrations amazingly do. So I'm not gonna say how this is defined, but essentially we do get a new predicate that is derived from, on the one hand, the standard notion of being a covariant family, and then on the other hand, the interval being tiny allows you to do a certain manipulation, which makes this into a meaningful construction. And then it turns out that the good model of the universe of spaces in this context is actually just as follows. Look at the universe U-simp, which is just the universe of simplicial types, the subuniverse of simplicial types from our cubical types. And then take the sigma type with respect to this universe, so just another sigma type, but now with respect to this amazing covariant predicate. And in fact, we can prove, using these additional axioms that I mentioned, that this candidate universe S now is actually not just a type, but it's simplicial, and it's an infinity category whose terms are infinity groupoids. It also satisfies the desired classification property with respect to amazingly covariant families. It satisfies the expected closure properties, and it's directed univalent. So the kind of geometric arrows in S do correspond to functors between two, kind of functions between its points being groupoid. Being groupoids means that that the functions are functors, and so arrows in the universe are functors, which is the directed analog of Blavatsky's univalence axiom, which says that like paths in the universe are isomorphisms or equivalences. And some crucial kind of ingredient that we need here is what's called the equivalence lemma, which basically says that if we have a natural transformation between two covariant families that is an equivalence at both ends, then it's actually an equivalence whatsoever. So for this, we need this kind of cubes generate or simplices generate theorem. And this whole argument is in some sense similar to earlier work by Weaver and Licata, who did a similar construction of this universe and proved its classifying property. But this was still with respect to kind of this older Lopes construction. And their axiomatization was different in various respects, including that for them, this equivalence lemma or theorem actually was an axiom, whereas we rather can prove it from kind of other axioms. Okay, so the way that this works is that, as is often the case, we have one kind of easy map in one direction, which is kind of about converting an arrow in the universe to a functor. So that works basically just by evaluation and then transport, for which we need the classifying property, of course. And then the other direction works by a kind of mapping cone or directed glue type construction, where we take a sigma type over the fiber, exponentiated by this proposition here. So those are two maps in opposite directions. One has to show that they form, that they are kind of mutually inverse. And this is also where we need the equivalence lemma. And interestingly enough, the way that we proved this was to first prove directed univalence, and then without knowing that the universe is actually Segal, and then proved kind of Segalness along similar lines, but using the equivalence lemma, but like in higher dimensions for higher simplices. At least that's how I remember it ended up going with respect to the order. Okay, what are applications of this? So we now get a directed structure identity principle, since we can define the category of spaces. So when I say category now, unless otherwise specified, I do mean infinity category. We can define the category of pointed spaces, and we can compute the Hom types by virtue of directed univalence to be, just functors that preserve the base point up to homotopy. Maybe more interestingly, we can define the category of monoids, set-based monoids at least. And again, the maps compute to being the expected thing, meaning monoid homomorphisms. But even more interestingly, we can now kind of start the development of synthetic higher algebra by looking, first of all, at presheafs. I mean, presheaf category now is just defined to be the functor category from the opposite of C to S. And for instance, the category of coherent monoids is a certain full subcategory of simplicial spaces. So simplicial spaces now internally to our theory. So full subcategories we can also define by means of the discrete and co-discrete modality. So in particular, as is kind of a standard way of defining these objects in like set-based higher algebra is to basically impose a certain Segal kind of condition from which you can then abstract multiplication in this way and then get all the higher coherences. Since this is just a proposition, because this is about some family of maps being family of equivalences, this defines a full subcategory. And yeah, I mean, we just can define, you know, by definition, it's a category. I mean, not quite by definition, but it ends up being a category for very general reasons. And I haven't stated this here, and maybe we didn't really write this down, but also for this category as much as the related category of infinity groupoid, which is another full subcategory of this, you could use, you could figure out what the Hom types are and what they should be in this like directed structure identity principle way using directed univalence. Another great object that we can define is the type of spectra. And because we have pointed spaces, we can define the loop functor. We can take the ordinary limit just in the sense of HoTT, and we can prove that this is an infinity category. In fact, it's stable and co-complete. I mean, the hope is that we really want to kind of reap the harvest from, you know, just having spaces as a universe for now, to go to town and do some higher algebra. So another feature that I promised is now the categorical Yoneda lemma as opposed to the fibrational Yoneda lemma that I mentioned earlier in the beginning. So the hard part is to kind of define the Hom functor, but we do the Hom bifunctor, which is supposed to have this signature, which actually is something where to even just express this, you really need to have an additional operation, because the Hom type former by itself as an extension type does not have this signature. Because there are no opposites. So, but with the opposite modality, you know, like this type makes sense. And from the twisted arrow, from the twisted arrows, we can prove that we can prove that the kind of type of the category of twisted arrows in a category naturally projects down to C cross C op, which I mean it does by our axiomatization actually, but we can prove that it's a left fibration, and so we can take its unstraightening, and this gives us the right Hom bifunctor, and we can prove the Yoneda lemma for this. We can also prove density of, like we can prove this density result that every presheaf decomposes as a co-limit of representables. And we can prove various nice things in general about presheaf categories, such as descent and the universal property as a free co-completion. So furthermore, we have developed the kind of first steps in the theory of Kahn extensions. So Kahn extensions are a universal way to extend functors along other functors. And the compact way to say is that in the case of left count extensions, that this reindexing has a left adjoint. We can prove the kind of classical co-limit formula for this. And this, like, rather naturally leads us into a study of final, or I mean left and right cofinal functors, depending on what terminology one prefers. So we call a functor right cofinal if precomposing like a co-presheaf leaves taking limits invariant. We can prove another characterization of this, which is often useful, meaning that this exactly corresponds to being right orthogonal to right fibrations. Sorry, to being left orthogonal to right fibrations, as shown here in the square, or being what's called a contravariant equivalence. So all these are kind of well explored notions already just in the homotopy theory of one categories, but in particular also for infinity categories, and we can replay them in our synthetic setting. So one classical result that we could also prove is Quillen's theorem A, which is a characterization of right cofinality in terms of this fiber here being weakly contractible, meaning its groupoidal localization is contractible. And we can prove this in a kind of nice modular way by reducing to the case of presheaves and ultimately the category of spaces. And one important result that falls out from this is what's called the properness of Cocartesian fibrations. So this says that if we have a Cocartesian fibration pi and we pull it back along a right cofinal map, then the pullback of that right cofinal map is itself right cofinal. And here we found a nice synthetic proof which kind of uses in a nice way this interplay between categorical and type theoretic reasoning. So to prove that this map is cofinal, is right cofinal, means that we have to compute a certain fiber, which by kind of co-Cartesianness, reduces to this object here. But then applying the localization to this fiber is the same as looking at the localization of this fiber, where this also is being localized. And but since this is contractible, we also get that the whole type is contractible. So here we're using results about the kind of internal theory of modalities or higher modalities in homotopy type theory. So that's kind of a nice slick argument. Okay, so as an outlook, we're definitely looking to do more synthetic higher algebra. We're also thinking about kind of generalizing our results that we have for the universe of spaces to that of infinity categories. A nice goal would also be to extend pre-existing formalizations in some way. Yeah, I think just developing actually more of the applications for which infinity categories traditionally have been used for, would be a good thing to look into. So there's a bunch of references that we're kind of relying on, many of which I've mentioned in the course of the talk. So if you want to look them up, that's where they collected. In particular, the formalization results the formalization of the Yoneda lemma that I talked about earlier, you can read about in this paper here. And then there are the two recent papers on the triangulated type theory directed to univalence and the Yoneda embedding together with Daniel and Ulrich. Okay, so thank you for your attention. I'm hoping we have a nice discussion.
Good. Thank you very much, Jonathan. So we will do either visual applause or you can use the reactions in Zoom. And we have plenty of time for questions. So if anyone wants to start, just feel free to unmute yourself. Okay, I will get the ball rolling. So you mentioned something about formalizing in your outlook. So is there any prospect for a proof assistant that implements this theory, or is that something too far off?
That's a good question. I mean, I'm hoping that people that have implemented proof assistants could tell me, but it would certainly. So I mean, so of course we have RZK. Currently, it's not really equipped to handle modalities. On the other hand, we do have. I mean, there's cubical agda, which maybe can serve as a platform for at least kind of analogous development in a more cubical setting. There are also some, I think, efforts by some people to develop like general multimodal proof assistants. So yeah, I think there can be many directions there.
Other questions?
Hi, can you hear me?
Yes.
Yeah, please.
So I was wondering, so first of all, thank you for the talk. I was wondering what's the relation between this kind of directed type theory and the kind of type theories that, for example, Newman and Altenkirch have been developing. So I'm referring to the synthetic one categories in DTT paper.
Yeah, so semantically, I think they're only aiming to capture basically one categories. Maybe it's a bit more general than that. So I don't know if you could also get internal categories or something. But certainly there, I mean, I think their goal for now, at least, is to just capture one categories. And their type theory is what I would call like genuinely directed, in the sense that their judgments have directions built in. So you can have like a covariant or a contravariant dependence. Probably they call it slightly differently. Whereas in our theory, or in this kind of original Riehl-Shulman type theory, which our theory kind of builds upon, but doesn't change. In that respect of directedness, is that well, we have directed shapes in the sense of there are certain axiomatically given posets, that are not like we have a directed interval that is not that is a directed interval, but the type theory itself, and then of course we do have kind of covariant and contravariant families, but the type theory itself doesn't capture in its judgmental form this sense of direction. It does maybe a little bit because we actually do have this opposite modality. So maybe this gets kind of blurred a little bit as we go along, but it's still just a proposition to be either or a covariant or a contravariant family or both. And in the Altenkirch-Neumann theory, it's really just part of the. It's like hard coded into the syntax.
Right. Thank you.
I see Martin has his hand raised. You're muted though. Martin Escardo?
Sorry, I started answering without unmuting myself. I'll start again. So I really enjoyed your talk, and it was really nice. So I have a kind of philosophical question and a practical question maybe. So one advantage of HoTT is that it gives a very simple and transparent arguments compared to when you work with groupoids compared to the usual way of doing things. So can you say something about the experience that you had when you formalized things with Emily and Mike about this? How does it feel in practice?
So yeah, so I do think that already earlier on, so in Emily and Mike's pen and paper work, that then with Emily and Nikolai and other people, we kind of started formalizing. You could already see like this, similar simplifications and strengths of like the syntheticness of the theory. So that goes back to partially the naturality for free that I mentioned earlier, which also is a feature of some of these other kind of directed type theories that I mentioned. You can prove that the type of natural transformations is, what you think it is. You get the naturality squares just by like unwinding the definition. When we proved the Yoneda lemma, so we discussed this a little bit more in the paper. In fact, in the paper with Nikolai and Emily down here, in fact, we compared our formalization of the fibered discrete Yoneda lemma in Rzk with a formalization of the one categorical Yoneda lemma in Lean that was contributed particularly for our case study by Sina Hazratpour, and also a version of the Yoneda lemma in univalent Agda, I think, by Emily. And the findings definitely in the Lean case, but I believe also in the Agda case, were that so the point that I made about this kind of proof being rather cheap in a certain sense, very kind of like very uniform, is because of that, right? So you don't have to show that this map actually defines like a natural transformation. You can just prove that you get natural transformations. You can just prove more generally that that this is something like fibered maps, which then can be also regarded as natural transformations. And so that was for, and this story also continued when we with Ulrich looked at the Cocartesian case. So I think there are also the proofs for so the proof that we had for the Cocartesian case, which currently is not formalized, but I think there's no significant problem in doing that at some point. That kind of paralleled a version of the corresponding statement in infinity cosmos theory, which you can find in Emily and Dom's book, Elements of Infinity Categories. But it turned out to be significantly like easier to write down and to understand, and more intrinsic. So it used kind of similar ideas, but you didn't have to care about kind of homotopy coherence or something, because everything is coherent anyway. And to the point of the more recent work with Daniel and Ulrich about the presheaf theory, Kahn extensions, I think it's all the more true there. So arguably the theory is a bit more complicated because you have to introduce these modalities, and I mean the type theory is kind of non-trivial if you want to set it up properly. But the hope, of course, at some point would be to have a nice interface that just takes care of you, takes care of this for you. And the proofs that we found, they're all intrinsic, so we don't need to kind of, as you would find in, the more older literature, change your model from whatever quasi-categories to simplicial categories, do something there, and then kind of reflect it back. So all of these things we do not need to do. And we do need to introduce some kinds of structure in the guise of these modalities, and we need to introduce some axioms, about the simplicial structure. But I think so far all these axioms can be mostly all understood to be kind of first principles from a certain point of view. And so in the future, I personally would hope that, we get a nice way of also enabling formalizations, at least of some of these more advanced results.
Dan,
yeah.
Thank you. Dan, can I ask a follow-up question given the answer?
Sure.
So you mentioned, so you hope in the future to get a nicer interface. So I would like to make an analogy here. So for example, we have a cubical AGDA and we have HoTT as in the HoTT book. And so cubical AGDA can implement univalence, it can implement higher inductive types and so on. But in some sense, at least in my view, the HoTT book is a better interface to cubical AGDA, just using the axioms univalence and higher inductive types. So do you have any idea in mind when you said a better interface of what you would be looking for?
So, right. Maybe part of it would definitely be kind of not all the time thinking about this like triangulated type theory where you have some cubical layer and some simplicial layer, because like the cubical layer is really only there to set things up. So I think, it's fine to have this kind of on paper, and it would be good maybe to also kind of formally verify this at some point. But then for just the actual infinity category theory, the idea is that this should really just take place on the simplicial layer, which probably is also true for everything that we've done so far. So that would be the first step, to kind of just strip this away, like this cubical layer, and then just work with, the classifier for left fibrations, or in the future Cocartesian fibrations, just like axiomatically, postulated to you. And then the other part maybe is just syntactic sugar to make annotations of like modalities and like the mode theory, as much hidden as possible and desired at the same time.
Okay, thank you.
Hey, Ian?
Yeah, can you hear me?
Yep.
Yes.
Okay, I just wanted to say thanks for the talk. This is something that I've been following since I heard about it on the AGDA Discord, so I was really excited to hear somebody talk about it. But I was curious, so earlier you mentioned some claims about the semantics of like the simplicial type theory before you guys added all the modalities and axioms and stuff. What are your guesses, or do you have any ideas about how the semantics will change once you add all this stuff in?
Yeah.
And this might be something you've kind of been touching on, but I just wanted to ask the question directly.
Yeah, it's a good question. So, yeah, of course it's, so we do at some point make some assumptions about the interval. So if you would like to work with kind of non-standard intervals, at some point this, becomes increasingly hard, which maybe is not so bad. We have this like duality axiom, which I'm not exactly sure how general it is. So that is probably something that has been well researched by the folks doing the synthetic algebraic geometry. So I can't really give a well thought out answer. For now, I think as a good like tentative goal is just to maintain the validity with respect to like the standard model, just with respect to spaces. But of course, it would be nice to, like allow for more general sheaf topos. And sometimes, you get things like, sometimes you also really need to do kind of homotopy theory, in particular when you're doing is like higher algebra, and so there maybe you need to rely on Whitehead's theorem at some point. You know, so that would be another like you know, that's just another non-trivial axiom that would rule out some models.
Okay, yeah. So thanks again for the talk and thanks for your answer.
Okay, we have time for more questions. Okay, well, if there's nothing else, I'll thank Jonathan again. Our next talk is in 2 weeks by Astra Kolometskaya. Notice that the seminar will meet 1 hour earlier because we're switching to daylight time in North America in 2 weeks. Or we're switching this Sunday, but it'll apply in 2 weeks. Okay, great. Thanks very much.
Thanks for having me. Thanks, Dan. Thanks, everyone.